Okay. This lecture is about the conceptual part of projectile motion. So, depending on when you're watching this today or yesterday in class, we discussed the monkey gun scenario, which is a classic setup for projectile motion. And what we discussed and hopefully demonstrated there is that an object in motion with some horizontal components, so some x component to its motion, will, without other forces, and we're not looking at things with engines and stuff like that, without other forces, will still fall vertically regardless of its x motion. So when we were talking about that with the monkey gun, we saw when I shot the two steel balls, one was shot horizontally straight off of the desk, and one just dropped vertically. Both of those things fell at the exact same rate. They fell in the exact same way, but one had some motion in x in addition, and the other simply had motion in y. And so that's the conceptual key to projectile motion. We would say that projectile motion works, and its behavior is explained by the fact that motion in x and motion in y are completely independent of each other. So again, that's the key point. Motion in x and motion in y are completely independent of each other. So what we're going to do is kind of talk about what's happening in x and what's happening in y and put that together. So this is, I'm going to do a lot of vector diagramming. We're not going to do any of the equations or anything yet in this lecture, so that hopefully you're comfortable with conceptually what is going on here. Okay, so I printed the notes so I follow the same order. Before we get into the vectors, I had three terms that I just wanted to make sure you were comfortable with. So there are three things, I'm sure they're words you've heard before. One is altitude, one is range, and one is trajectory. So again, probably you have a sense of what those are, but you'll see those terms used in the problems, and so I just want to make sure that we're good with that. So altitude is a term that's referring to, I'm sorry, can't talk, vertical height, for lack of better words. Range would be the horizontal displacement. And trajectory is sort of just a fancy word for path. So they'll refer to an object's trajectory, they're just talking about its path, the trajectory of the projectile, just showing us where it's going. If you are asked to find the range of a projectile, or they give it to you and you maybe use it in a problem, this is its horizontal displacement. So I said I'm going to refer a lot to sports. I don't know if any of you watching play soccer. If you kick the ball from the ground, and let's say nobody's in your way, and it goes 20 yards downfield, that would be the range of that projectile, the range of the kick. So we don't, you could do that and it could stay 2 feet off the ground the whole time. You could do that and it could be one of these kicks that goes up twice my height and lands downfield. That doesn't matter if we're talking about range. All we care about when you're referring to this term is where does it end up in x. So range is something we use mathematically when we're looking at motion in x. And then altitude is sort of the opposite. Altitude has everything to do with y. So if you're asked to find the altitude, or if they give it to you, they're referring to something's vertical position. So generally height is the word we would use to describe that as well. But we're saying where the trajectory is, or the projectile is, I'm sorry, in terms of its vertical motion. Okay, so let's look at that x and y. And so the next slide, I think, in your PowerPoint has the x and y components of a projectile's motion. So if you have something, there's all kinds of different trajectories that a projectile could take. I'm just going to go with the classic. It looks pretty parabolic. So something goes up and it comes back down. And I am going to diagram what's happening with the velocity. So let's say I kick something, a ball or whatever. It has an initial velocity, some initial velocity v naught, and it's kicked at an angle, we could say theta. And so as the object goes up It follows this. I'm just using arrows to indicate its motion. Hopefully you can see this on your screens. So this is black if you can't see a black marker. And so I'm just again following the path with these arrows. And so this I'm going to call the black will be my total velocity. And by total velocity I mean if you look at these arrows, they're pointing up and to the right for a while, then just to the right, and then down and to the right. So what we see happening here is these arrows or vectors are indicating a velocity both in x and in y, right? So it's a two-dimensional motion, which is what we're getting into. Now, what I'm going to do is go through, and again, this should be drawn. If you're looking at the guided notes, it's there drawn for you, so you can just kind of follow along. And I am going to draw the x and y components of each of these arrows. So I'm going to use blue for my x. So we'll say x velocity. This is your horizontal velocity. And I'm going to use green. Hopefully my kids didn't drain these. Yeah, good. And I'm going to use green to indicate my y velocity. So I'm just going to make a little right triangle out of each one of these vectors. So first I'll go with the x, which is the blue, right? Yeah. So here's an x component to the right, to the right, to the right, to the right. This is just all an x right here. So I'm just kind of drawing it right on top of the black line so you can see that. And then as they keep going down, there we go. Okay. And so what we're meant to see here is that my x velocity remains constant. And this is true for every projectile. The exceptions would be if you had something with an engine on it, right? And we're just simply not doing that right now. That's actually rocket science, one could say. So the velocity in x for every single projectile motion problem we see, and remember, I mentioned this in class, projectile is when it's in the air. There's no other forces acting on it, it's just in the air. The velocity in x will remain constant, and that's huge when we go to do the problem solving. So in class, when I was talking about, I was referring to running off of a diving board, or in a more dramatic way, driving off of a cliff, which we would never do, of course. Once you're in the air, so you're into your projectile motion, there's nothing you can do to change that horizontal motion. It is what it is. And so that's what's happening here. We have an x velocity that remains constant. Now, our y velocity, I'm going to use the green for the y. So we see it going up. And what we notice, if I draw these little triangles, as it goes up, right here at the top, it's 0. So I'm going to say Vy is equal to 0. As it goes up, the green arrow, which would indicate the vertical component, is shrinking. And then as it comes back down, that green arrow is growing larger and larger. So the y velocity is changing. X is constant, y is changing. And it's changing because the object in y is in free fall, which is what we discussed in the last chapter, right? So the vertical component of motion is impacted by gravity and gravity only. So we would say that this object is in free fall. And so if we kind of take this further, we would say the acceleration in x is always 0 meters per second squared, because we have that constant velocity in x, it's not changing. And the acceleration in y for a projectile is always negative 9.8. It's falling just according to gravity. So this is how velocity works with projectile motion. When we get to the problem solving, which will not be in this lecture, but when we get to the problem solving, what we'll see is because x and y are independent of each other, we'll set up and solve with x and y separately. Again, this will make more sense when I do it. But this is key. We will know that we have an acceleration in x that is 0 and a velocity that's remaining constant. And no matter what type of projectile I have, the acceleration in y will be negative 9.8, and we're going to see that the velocity in y is always changing as the object falls. The other thing to notice here is that at the very top of the projectile, the very top of its trajectory, the object does not stop. It stops in y, So there's that change in direction, just like we saw in the last chapter. When it goes from up to down, it stops in y very briefly for that brief moment, but it never stops moving in x, again, because we have that constant x velocity. So even though you have a stop in y at the top, the trajectory shows that the velocity never is actually totally zero because it's moving in x. Okay, so that's the big, this is, of all the diagrams, this one is the most important one in terms of your conceptual understanding. So this is the big setup for projectile motion. Now, I threw two more diagrams in your notes, one showing the acceleration, I think. I gotta flip my page and see. Yeah, the acceleration and the velocity. And if you have it on your screen, it's going to be in color. If you've printed it, it's black and white. And then the other showing some trajectories. Okay, so they're sort of just restating what we just did. So that second diagram, again, is just really restating. If I have the same, let's take the same projectile. So something that I've shot up with an initial velocity at some angle. It's going to go up, it's going to come back down, but it's moving across a field or some distance in x. If I draw my velocity vectors, again, I'm just doing the total velocities. So that's what you see on that diagram, just following, it follows the path of the projectile. So the velocity is always, we would say tangent to the path. Okay, so here I have these arrows just to redraw what I've done. This would be the velocity. They're different colors on the PowerPoint, but on my board, black will be the velocity. And the acceleration, if I want to draw the acceleration vector, the acceleration is just always straight down because there's no acceleration. Here, let me diagram it here first. There's no acceleration in x, and there's a constant acceleration of negative 9.8 in y. So I'm not drawing components because it's a totally different vector. It's not like this is a piece of this. But if I'm diagramming acceleration at every point, this is what it would look like. Straight down, and we would see that its magnitude remains unchanged. So I'm not sure, you know, some of you that might be a helpful visual, some of you perhaps not, but I threw it in just so you could see. The important part here, velocity, this is total velocity. This is not split into x and y like what we were just doing. Total velocity is just going to follow the path, the trajectory of your projectile. Acceleration, total acceleration is only in y. It remains constant all the time, which is why we can mathematically solve it. So remember I mentioned in the last chapter, if your acceleration is changing, you have to use calculus, and we're not there yet. So the constant acceleration of negative 9.8 everywhere, every single spot on the projectile's path allows us to solve it algebraically. Okay, and then the last thing I have in the diagram, you're going to explore this a little bit more Wednesday in your group work. It's just showing you the trajectories of some different angles, and they're sort of sketched out. And I'm not going to sketch the entire thing. I just want to point out, you know, on the board I'll be a little bit sloppy with it. Just want to point out, if you take something and you give it the same initial velocity, so in that, let's pretend the initial velocity is 10. If I shoot it at a low angle, its trajectory might look something like this. If I shoot it at a high angle, its trajectory might look something like this. Without air resistance, your ideal angle to get your maximum range is about 45 degrees. Again, I want you to explore this a little bit. We're using the simulation on Wednesday morning, so I'm not going to speak too much about it yet. But what I will say is the time in the air, the time that the projectile is in the air, is determined by its y component of velocity, so by its vertical motion. So this trajectory would be in the air a longer time. Think of if you've ever played baseball or softball. If you hit a ball that's a pop fly versus a line drive, right? Pop fly is nice and easy to field, generally speaking, because it's in the air for a long time, so you can move around and get yourself right positioned under it and catch the ball. So it's usually, for instance, at like the professional level, it would be an error if a player weren't catching a pop fly. Line drive, on the other hand, for many reasons, but a line drive would be a hit a lot of times, and the player will get the base. So it's harder to field because generally it's hit harder, so it has a bigger velocity. But the other thing is it's in the air, you know, it's hit at a low angle, so it's in the air a shorter amount of time. So the vertical is what tells us how much time the thing is in the air. The horizontal, the bigger that is, the further it can get. But if it's all horizontal, it's not in the air very long at all. So these things sort of can balance out a bit to give you what will be your range. So you'll also notice on the diagram, again, I want you to explore this, and we're going to talk about it in class on Thursday. So I'm just waving my hands at it for now. Some angles will give you the same range, and there's a pattern to what those angles are. So in other words, there's, if I look at my trajectories, there's 2 different angles that I could fire something to get to the same spot. So that's something you're going to mess around with this Wednesday morning, and then we'll talk about it in class on Thursday. So for now, I'm going to stop. That's all I have to say conceptually about projectile motion, and then the next lecture we'll dive in and explore some of the math and how we can begin to problem solve with it.